All right, so right now we're going to work on completing the square. Some of you, I would imagine most of you have done this before, but if not, we're going to review everything. We're looking at pages 91 and 92 in your packet. Okay, so that's graphs of quadratic functions. Let me make sure this is focused. Okay, so we're just going to kind of go back to the basics. When you square a binomial, and remember this, the Algebra 2 pledge, squaring does not distribute. Exponents do not distribute over addition. Okay, what that means, I can't just square the first term and square the second term. When you square a binomial, you've got to distribute. So 3x minus 5, 3x minus 5. I know you all know how to do this, but what we're doing is establishing the pattern so we can recognize the pattern. So completing the squares, we kind of do the patterns in reverse. So you have to recognize the pattern. So when I distribute or FOIL, 3x times 3x is 9x squared. And I do the outers. 3x times negative 5 is negative 15x. And then the inners, negative 5 times 3x, well, that's another minus 15x. And then the two lasts, negative 5 times negative 5 is plus 25. Then I can combine my two like terms. I'm just going to put my answer up here. 9x squared minus 30x plus 25. Okay. So what you'll notice is this first term in your binomial, when you square that, that's your first term. 3x quantity squared is 9x squared. When you take this negative 5 and square it, negative 5 quantity squared is 25. Now we have to look at where this middle term comes from. And what it comes from is the double, because where there's two of them, of these two. And where these two things come from is when you multiply the two terms in your binomial together. Okay, 3x times negative 5. Notice why that happens. You've got pattern. You've got the same binomial twice. So when you're matching up the first term with the first one with the second term in the second binomial, it's really just these two numbers. And again, when you're doing the inners, it's the same thing. It's the same two numbers. Let's look at this one. Okay, so when we distribute this, 2x plus 7 and 2x plus 7. 4x squared. And the outers and the inners, we've got plus 14x, plus another 14x, and then plus 49. So the 2x, this first thing squared was the first term. This thing squared was the last term. We have 4x squared plus 14x plus 14x, 28x, and plus 49. Okay. So let's now go backwards. We have to kind of work backwards here and say, okay, I know in order for this thing to be a perfect square, just like this trinomial up here is a perfect square. So basically what I'm doing, I'm trying to move backwards from this to figure out what squared binomial gives me this perfect square that ends up being a trinomial. What binomial will look at this and figure out work backwards, okay? So if you look at this, you know that your two terms in your binomial are going to be the square root of this and the square root of this. Square root of this is 2x. Square root of this is 7. So you know it's a 2x and a 7. Here we know that these two terms, if it is a perfect square, square root of this has to be our first term. Square root of 9x squared is the 3x. Square root of 25 is the 5. And then this thing is going to help you figure out if it's plus or minus. Okay, so we know that this is a perfect square. So we know x has to go here. Okay. We also know that this thing, where this middle term came from, it came from these two things that were our outers and our inners. Where this 28 came from, there were two 14x's that came from the outers and the inners. So we have to break this down. X squared plus 6x plus 6x plus something. Okay. But we know where the 6x came from. It was the first term times the last term. So this has to be a 6. Okay, so when we're going backwards, and then this last thing is going to be the 6 squared, so 36. Okay, so in order to get this thing, what we did, we took the 12x, we had to split it in half, and then we had to square it. So whatever this coefficient is of our x, we split it in half, becomes a 6, and we square it. And you could double check that that works. Okay, so basically what we did, we had to figure out what number needs to be added to these two terms when we have a quadratic term and a linear term, what constant would need to be added so that we have a perfect square binomial. Okay, now let's look at this one. This one's a little tricky because this is not a perfect square. Okay, and we got a little hint over here. We're just going to factor out the 3 at the beginning. We're going to factor the 3 out of both of these terms. And what's left? X squared minus 10x plus something is going to equal 3 times our perfect square. Okay. Now we're going to take half of this coefficient. Remember when this got split up, the outers and the inners, it was a minus 5x minus another 5x. And that number is going to be your second number. But that number squared is what goes here. So half of this is 5, square it, you get 25. Okay. So if you wanted to figure out what actually goes here, this was the 3x squared, this was the minus 30x, and this is the plus 75. Okay. That's not an important part. The important part is figuring out what goes here. Okay. This is a perfect square binomial. X is the first term, 5 is the last term. We know there's a minus. Okay, x minus 5 quantity squared. The pattern is going to be the first one squared, multiplying these two together, and then doubling it gives you the negative 10x, and then the 5 squared gives you that. Okay, so let's go practice a couple more. Okay, now here we can solve by completing the square. There's 2 reasons you might complete the square. One is to solve an equation. Okay, second one would be to put something into vertex form, like what we're going to do down here. This is way more useful, and we're going to focus more on this, okay? But we're going to do this one first to focus on completing the square. Some of your Delta Math assignments, you're going to be completing square kind of in this pattern, and that's what you'll be doing tonight, okay? So notice what we did up here. When we wanted to figure out that constant that we add to complete the square, well, this already has a constant here. But that doesn't look like the constant that's going to complete the square. So let's move it over. I'm just going to move it over to the other side. So instead of minus 20, the other side is now going to be a positive 20. I just added 20 to both sides. What number here completes the square? Well, we take half of this term, which is negative 4, and you square it. You get plus 16. Okay. Now, this one's an equation. You can't just add a number to one side of the equation. It makes your equation untrue. So we have to add 16 to the other side of the equation to keep it balanced. Now we can rewrite this as x minus 4 quantity squared is equal to 36. Okay, so there are a couple Delta Math assignments where you're going to leave your answer like this. It explains that in the instructions. Okay, and then there will be some, I don't remember, there might be some that you also have to then solve the equation. So here, now we're going to solve the equation. We're going to square root both sides. So we have x minus 4 squared equals 36. We're going to square both sides, square root both sides. Square root goes away. We've got x minus 4 equals plus or minus square root of 36. Okay, so x will equal positive 4 plus or minus 6. Okay, and that we can simplify. So x equals 4 plus 6, or x equals 4 minus 6. Okay, so 10 or negative 2. Okay, so this is another method to solve this equation. Maybe you looked at this and oh, that factors. That might have been a lot easier to just factor. Well, you could, but we just learned another method. Okay. Now, for the following equations, complete the square to transform from standard form into vertex form. So vertex form looks like this. Now notice the difference with these equations. We have a y in them. So we have a y, and then we want to get it into this form where we've got a perfect square. The reason we do that, because when this equation is in perfect square, the number that's in here, that's being subtracted from your x in your binomial that's squared, is the x coordinate of your vertex. And this number over here that's added, the plus k, that's the y coordinate of your vertex. And then your axis of symmetry looks like this. And once we know that, these are going to be really easy to graph. Remember, anytime you graph a quadratic equation, you get a parabola, something that opens either up or down. Okay, so let's do this. Let's convert to standard form. Now notice, you've got a y here on the left side. So we're going to leave that alone on the left side. Here we've got the x squared minus 6x. Does this plus 5 complete the square? Does that make this a perfect square binomial? I don't think so. Okay, so we could do, I'm just going to move it over. Notice it's still going to be plus. I'm not moving it to the other side of the equation. I'm just going to slide it over. So over here, it's still going to say plus 5, but I'm just going to move it over. Now we want to figure out what will complete the square here. So now we're going to do what we did before. We want this thing to be a perfect square binomial. So we complete the square by taking half of this coefficient, which is -3, and squaring it. So we get plus 9. Now my equation is not balanced. If I add 9 to one side of the equation, I have to also add 9 to the other side of the equation. But instead of doing that, I'm going to add 9 here, and then I'm going to subtract 9 here. Notice I'm adding 9 and subtracting 9 on the same side of the equation. So therefore, I just added 0 to the right side of the equation. That makes sense. You can add 0 because of your inverse property or identity property of addition. Okay, so now you've got your perfect square, x minus 3 quantity squared, and then you've got minus 4. Okay, this now is in vertex form. Okay, our vertex form is y equals x minus 3 quantity squared minus 4. Okay, the vertex is positive 3. Notice there's already a minus 3 in the formula. This h is whatever's being subtracted from your x. So if that was an x plus 3, your h would be negative. But since it's minus 3, your h is positive. And then this thing, that's just a plus k. So your k value is negative. Your axis of symmetry, that's a vertical line. It's x equals whatever your h value is. Okay, so the 3 here. It's kind of easier to see when you draw it. Okay. So our vertex is 3, -4. Now, our a value is a positive 1. And when our a value is positive, we know that it's opening up. Okay. And then we can find our x and y intercepts. Okay. So let's actually do this. Let's find our y-intercept. So our y-intercept happens when the x is 0. When x is 0, then hit 0 minus 3, which is -3. -3 squared is 9. 9 minus 4 is 5. So 0, 5. And 1, 2, 3, 4, 5. And a symmetric point just means like the mirror image point on the other side of your axis of symmetry. Our axis of symmetry is x equals 3. So we usually draw that as a dotted line. Our symmetric point, usually we find the symmetric point with the y-axis. Okay. So it's the mirror image on the other side of your axis of symmetry. Okay. And then your x-intercept, well, that happens when y is 0. So that's going to be something, 0. So we could solve that. I'm just going to solve it down here. 0 equals x minus 3 squared minus 4. Add the 4 to the other side. Square root both sides. We get x minus 3 equals plus or minus 2. Square root of that would be x minus 3. Square root of that plus or minus 2. So x is going to equal 3 plus or minus 2. So 3 plus 2 or 3 minus 2. So we have 5 and 1. So 5, 0, 1, 2, 3, 4, 5, and 1, 0. Okay. And because of our pattern, we're going to talk about kind of a rapid way to plot parabolas. We know that there would be another point here. Hopefully you recognize that pattern that when you've got parabolas, when you've got a parabola and your A value, this value right here is a positive 1, the pattern is over 1 up 1, over 2 up. Oh, this isn't right. What did I do wrong? Oh, here's what I did wrong. That should be a -4. The vertex is a -4. I just plotted it in the wrong. I plotted it at -3, so it should be down there. Okay, and this should be over 1. That makes sense. Don't forget your arrows. Okay, so your pattern for a parabola when your A value is 1 is over 1 up 1. Okay. If you went over 2, you'd go up 2 squared, which was 4. Over 3, you'd go up 3 squared, which is 9. Okay, so some of you have probably seen this pattern. Another way to see this pattern is by looking at going from your previous point. So you could go over 1 up 1. From here, you go over 1 up 3. From here, over 1 up 5. And then from here, over 1 up 7. So you've seen that pattern, maybe 1, 3, 5, 7. Just go up odd numbers. Okay. I actually would like to talk about kind of how to plot these quickly. Maybe we'll do these on the other pages in the next video. But I want to talk about this real quick. If you go back to page 86, okay, and I'm going to go over what I just talked about here, but a little bit, I'm going to slow it down a little bit. Okay, so the first one, you have y equals x squared. If we made a table of values, let's just do -3, -2, -1, 0, 1, 2, 3. Okay. Notice what your y value is. It's whatever your x is, but squared. So -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1, 4, 9. Okay, our vertex is at 0, 0. We've got 1, 1, and -1, 1. Got 2, 4, -2, 4. 3, 9, and -3, 9. So this is the pattern I was talking about. If you're measuring from your vertex, you'd go over 1, up 1 squared. You'd go over 2 from your vertex, up 2 squared. Over 3, up 3 squared. But the more interesting pattern is the odd numbers. This is a pattern, since our A value is positive 1, of 1, 3, 5, and then we go on to 7 and 9. Okay, this is going to make things a little bit easier when you want to plot a parabola quickly. Now let's look at this one. What happens when our y value or our A value is 2? Now notice here, if you think about this in vertex form, so y equals A times x minus h squared plus k. So if we wanted to write this out, that's y equals 2 times x minus 0 squared plus 0. Notice there's nothing subtracted from the x before you square it. So your h is 0. There's nothing added over here. So your k is 0 and your vertex is 0, 0. Okay, now this pattern still works, but it's not 1, 3, 5, 7. It's actually 1a, 3a, 5a, 7a. Okay, so our a value is 2. So we'd go over 1, we'd go up 1a, 1 times 2, so we go up 2. And from this point, normally it's 1, 3, so it would be 3a, 3 times 2. And we're going to quickly be off the page, but this just rises a lot quicker because these values, and this pattern always works as long as you know vertex and you know your a value. So that was over 1 up 1a, over 1 up 3a. The next one over 1 up would be 5a. So 5 times 2 would be up 10. Okay. So let's go down. Let's look at the next one. We can do these fairly quickly. Okay. So now here our A value is 3. Let's find our vertex. Vertex is 0, comma, negative 10. Now our A value is 3. So from here, we're going to go over 1, up 1A, which is 3. And then from that point, over 1, up 3A. 3A would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the symmetric point would be over here. Okay. And then from there, we go over 1, up. Remember, it's 1A, 3A, 5A. So 5 times 3, you go up 15. Okay, we're going to be off the page, way up here somewhere. Okay. If that's really easy, you can always make a table of values and plug them in. This is just an easier way. Up 1A, up, that's 3A, and then up 5A. Okay, you just keep going with the odd numbers. Okay, so something like this. Now that we're in vertex form, our vertex is 1, comma 5. Now this one opens down, so the 1A, 3A, 5A still works. 1, comma 5 is right here. Now A is negative 2, so 1A would be down 2. From that point, 3A would be down 6. The symmetric point would be over here. And 1A, 3A, 5A would be down 10. So we'd be going down to, where are we here? 1, 2, 3, 4, 4, negative 13. Okay, and then there'd be another one over here at negative 2, negative 13. All right, sounds good. So that pattern can be very useful. Okay, and then, oh, and one thing I didn't write in on this first one, I remembered I didn't write in our symmetric point. You can't have a symmetric point by itself. Any point can be a symmetric point with another point. So a lot of times we use our y-intercept and the symmetric point with the y-intercept, which would be this point over here. So this point is 0, comma 5, and this point would be 6, comma 5. So 6, comma 5, and I'll usually say symmetry point of 0, comma 5. Okay. All right.